Now we're going to talk about the breakdown of the adiabatic approximation. Of course, when adiabatic approximation breaks, then of course you no longer have Born-Oppenheimer approximation. So this is actually extremely important. It's important for photochemistry, for instance. For the understanding of the excited state dynamics, quenching, phosphorescence, etc., you need to understand the breakdown of adiabatic approximation. And for discussing electron transfer or charge transfer, you also need to understand the breakdown of this adiabatic approximation. And you will actually use not the adiabatic basis, but the so-called diabatic basis to talk about electron transfer in Marcus theory, or to talk about proton-coupled electron transfer. All right. So actually, you already know that why the adiabatic approximation breaks. It all comes from the coupling element, CHI, right? So if delta V, this is, let's use notation in the adiabatic approximation, V is the electronic eigenvalue plus the CII, the diagonal correction. Delta V is simply the gap between two different V, okay? You can have state 1 and state 2, then what's the gap between these two? This delta V means the gap. Or this is simply delta E, the gap between different electronic state, as in the Born-Oppenheimer approximation. So in the Born-Oppenheimer approximation, we don't have CII, and therefore the effective potential for the nuclear motion is simply equal to the eigenvalue of the electronic Schrodinger equation. When this delta V is smaller or comparable to the kinetic energy of the nuclei, then of course, the adiabatic approximation breakdown. So usually this is because you have delta V is very small. Sometimes delta V is even equal to 0. Then of course, around this region, you can no longer apply the Born-Oppenheimer or adiabatic approximation in general. So this coupling element, for psi j gradient, for psi I electronic, so which is part of the definition of the baryon connection, can be actually calculated by using for psi j electronic, the nuclear gradient times the electronic Hamiltonian for psi I electronic over EI electronic minus EJ. So I will not prove this formula here. I actually put it in one of the problems in your problem set. The point is here that you see this coupling element is proportional to 1 over delta E, right? This delta E, the gap between different electronic states, is on the denominator. And therefore, if there is no gap between the electronic states, or if the gap is very small, this coupling element is going to be very large, right? And this will cause difficulty in studying the nuclear motion. Because when you try to solve the exact nuclear equation for the studying of nuclear motion, of course, if you have a term that is close to infinity, very, very large, then how can you solve this equation, right? So this will cause great difficulty. And of course, the study of nuclear motion is essentially the study of chemical dynamics. So this is actually a very important question. So let's just see two simple examples. For instance, let's see a diatomic molecule. V electronic versus the interatomic distance. Let's consider, say, sodium chloride. This is a typical diatomic molecule. Let's consider the diatomic sodium chloride. Okay, it's not a crystal, but it's a molecule in the gas phase. Now, of course, the electronic Schrodinger equation can be solved, and of course, not exactly, but approximately. And if we consider only the two states, the solution looks like something like this. Okay, this is the solution. So you have two electronic states, state 1 and state 2. Okay. But at this point, which is at the equilibrium bound distance, the character of this sodium chloride molecule is really ionic. So you really have sodium cation and chlorine anion. This is the ionic character. Meanwhile, at the same distance, at the same equilibrium bound distance, the excited state here really corresponds to a covalent structure. So this excited state is actually a covalent sodium chloride. You have a pair of equally shared electrons between sodium and chlorine atom. And if we look at the ground state here, the lower curve is for the ground state. At the dissociation limit, when you dissociate this sodium chloride, you will get sodium atom plus chlorine atom. This is the dissociation limit. Okay, this is the product when you try to dissociate sodium chloride. You will get two atoms. But the excited state would be sodium cation plus chlorine anion. This is the excited state. Okay, so difference between these two, of course, is the first ionization potential of sodium atom and the electron affinity of chlorine atom. Okay. Now, you will have, so in this region, these two states are very close. Of course, in order to make sure that you indeed see this region, I kind of make this region larger, but actually this region is pretty small. The gap is pretty small, but not zero. Not zero. This is not zero. This is non-zero gap. Okay. So this gap is actually called the avoided crossing. These two curves do not cross, but they are separated at this region by a small gap. This region is called the avoided crossing region. So imagine first you do the experiment, okay? Imagine you prepare a ground state sodium chloride in the gas phase. And you can use light to excite this molecule to the excited state. And of course, the atoms move on a particular potential energy surface, right? So now the atoms move along this excited state potential energy surface and reach this region. Now it has two choices. One choice is remain at this excited state surface, and you get sodium cation and chlorine anion as your product. This is, of course, the adiabatic approximation. But in this region, in this avoided crossing region, because the gap between the two electronic states is very small, if we look at this formula, you will have a very large coupling elements. The coupling is very large. It's not ignorable. And actually what happened would be that this excited state will jump back to the ground state. At least part of the system, part of the molecule, some of the molecule in the system will jump back to the ground state and then move along the ground state surface adiabatically. So you will actually have two different kinds of products: sodium atom plus chlorine atom and sodium cation plus chlorine anion. So the jump occurred in this avoided crossing region is actually non-adiabatic. Okay, sometimes people call it a Hawking event. This is non-adiabatic transition between the excited state and the ground state. Okay. In general, this occurred very frequently on higher excited state. When you study a system and you excite a system to a higher energy level, okay, and then the system will follow the excited state potential energy. If you have such avoided crossing region, then you will have non-adiabatic transition. This is actually very common in the excited state dynamics when you study photochemistry. Photochemistry essentially is the chemistry of excited states. Okay, this non-adiabatic transition is actually because of what? Because of this very large coupling element, this very large non-adiabatic coupling element due to the nuclear motion, right? Okay, this is the example of a diatomic molecule. In general, if we study a polyatomic molecule, for a polyatomic molecule, of course, this function V electronic, or in the case of Born-Hamer approximation, E electronic, is multidimensional. So we cannot really draw a full potential energy surface, but we can focus on a particular dimension. Say this dimension is S. Let's consider a polyatomic molecule. So this S is just a particular dimension. So imagine you can have this scenario, in this case. You still have two states, okay? State 1 and state 2. So at the equilibrium, so this is the equilibrium. At the equilibrium, you have two states that are very well separated. And therefore, at this region, definitely you can apply the adiabatic approximation, or you can apply the Born-Hamer approximation. Imagine you excite this system from the ground state at the equilibrium geometry to the excited state. Then the system follows the excited state surface until it reaches this region, reach this point. So you really have a crossing point, okay, in which the gap between these two states is exactly equal to 0. At this particular point, you have degeneracy. Of course, one way is that you stay on this surface. That's one of the possibilities. Another possibility is actually through this crossing point, the system cross to the ground state. So this crossing point is not simply a zero-dimensional point. It's actually, well, in a multi-dimensional surface, it's so-called conical intersection. I should draw this cone like this. Because in the vicinity of this crossing point, actually the change of the potential end surface is somewhat linear, actually. So here you have a cone here, a double cone. Okay, because, well, this is actually a multi-dimensional surface. If you really write down the equation for this crossing point, geometrically, it corresponds to a double cone. So this is called the conical intersection. Okay. So in this, exactly at this conical intersection, the difference between the electronic state is zero. There's no energy gap. And therefore, if you look at this coupling element, if the denominator is zero, then this coupling element is singular, right? So this is the singularity point. If you have a singularity point in your equation, it's extremely hard to solve this equation. Of course, when we talk about simple system, one-dimensional, exactly solvable system, we talk about how to remove the singularity point. But in general, for a polyatomic molecule, when you solve the nuclear motion, you cannot do that, okay? Because the equation is not really analytically exactly solvable. Usually what we need to do is to use numerical method to solve the equation. But the point is, if you have this singularity content there in your equation, it will cause great trouble, okay? Especially when you study the dynamics process. So at one region, say around the equilibrium geometry, you have no problem solving the equation. You can just propagate the nuclear dynamics as usual. But when you reach the vicinity of this conical intersection, you have great trouble. You have a very, very large term, and at this conical intersection, when the system hits at this conical intersection, you will have a singularity. Of course, the probability of the system actually hit this exact conical intersection is extremely small. But around the vicinity of this conical intersection, you will have a very large coupling element. Okay. So for these two cases, actually this is already very general, you can no longer apply the Born-Hamer approximation. Okay. So around this region, in which you have very tiny gap between the two electronic states, you can no longer apply the Born-Hammer or adiabatic approximation. But you do not really need to abandon the concept of potential energy surface completely, because it's really just around this region, right? It's a local property. You can still propagate the system along the potential energy surface, but it's just around this region you can have a non-zero probability for this quantum mechanical hopping events, so that your system can hop from one surface to another surface. Okay. And around this region, as we can see here, for instance, for sodium chloride, the character of an electronic state change rapidly, right? So let me just draw another trajectory here. So, so here, from here to here, your system is ionic, okay? The wave function is ionic. But from here to here and to the dissociation limit, you have a covalent wave function. Around the avoided crossing region, actually, you will have a nearly one-to-one mixture of the covalent wave function and the ionic wave function. So you will have a sudden change around this region. Similarly, for a polyatomic molecule, for instance, if the character of the wave function is A, here is B, and so by crossing this conic intersection, the character of the wave function switch from A to B rapidly. Okay, you have this sudden switch. Well, actually, it's not sudden. It's a smooth transition, but you have this switch of the electronic state. Okay, this is the character of the electronic wave function around the vicinity of an avoided crossing or a conic intersection. So of course, then it's really not convenient to solve the nuclear dynamics. So we need to use another representation instead of the adiabatic representation. So let me draw this sodium chloride case again. Okay. Just pictorially, it's like this. Okay. Of course, the green curve here are the adiabatic surface. Right? This is the adiabatic surface. For the adiabatic surface, the electronic Hamiltonian is diagonal. Right? The electronic Hamiltonian is diagonal. Okay. Of course, this region is the avoided crossing. So at the left, you have the wave function has a particular character, say A. The character of the wave function is actually characterized by the configuration coefficient. You can expand the electronic wave function in terms of multiple configurations. And the linear combination coefficient characterize the importance of a particular configuration. And this gives you the character of a particular electronic wave function. We will talk about this expansion in the later of the lecture, but here I just want to briefly mention it. So here you have character A, and for the excited state, you have character B, right? In terms of the, for instance, for sodium chloride, then character A is ionic, character B is covalent. And now at the dissociation limit, the ground state is character B. The wave function of the ground state at the dissociation limit is character B. And the excited state becomes character A. Okay? So if you follow a particular adiabatic surface, then around this small gap region, around this avoided crossing region, you have a change, a rapid change of the character of your electronic wave function. Another way to construct a surface, a smooth surface, is to use the so-called diabatic surface. So when you are far away from the crossing region, for the avoided crossing region for a diatomic molecule, for sodium chloride in this case, then the diabatic surface is essentially very close to the adiabatic surface. And during this region, you will have this transition here. And for the higher energy surface, when we reach this region, okay. So the pinky curve here, the pinky dashed curve here is the diabatic surface. So along a diabatic surface, so if you start from here, it's character A, and then you move along the diabatic surface, you see, you always have character A. Similarly, if you start from here, then you move along this diabatic surface, you always have character B. So you have the same character at OR, at all the nuclear coordinate on a given surface. So the character the character of the electronic wave function does not change. Okay? But the electronic Hamiltonian is not diagonal. Okay? So when you use this diabatic representation, the electronic Hamiltonian is no longer diagonal. And in general, for a polyatomic molecule, the nuclear derivative coupling is much smaller than the off-diagonal element of the electronic Hamiltonian. So you see, you no longer have this problem of singularity or very large nuclear coupling. The nuclear coupling becomes very, very small. This coupling element is very small. Then, of course, you can propagate the system on this diabatic surface. This is, by definition, the diabatic representation have these properties. Okay. So For a diatomic molecule, in the case of sodium chloride, the two adiabatic surface, they do not cross, they avoid. And the corresponding diabatic surface, they cross at a point, okay? But for the diabatic surface, the nuclear derivative coupling is much smaller than the off-diagonal element of the electron continuum. And therefore, you have no trouble in propagating the system trajectories. Okay. In general, a diatomic molecule actually can cross, the adiabatic surface of a diatomic molecule can cross. That depends on the symmetry of the electronic wave function. But for sodium chloride, they do not cross. Okay. So if we consider another situation, for instance, a polyatomic molecule, and we have a pair of crossing potential energy surface. Okay, so if the adiabatic surface are crossing with each other at this particular conical intersection point, then the corresponding diabatic surface avoid this crossing. Okay. But again, on the same diabatic surface, you have the same character all along at any R. Okay. So naturally, you wonder how to find this diabatic surface based on the adiabatic surface. This procedure is called diabatation. The goal of diabatation is to try to find a linear transformation to transform a set of adiabatic bases to diabatic bases. So a diabatic basis, for instance, can be written as a linear combination of the adiabatic bases. K depends on the number of adiabatic bases you have. Okay, so phi k here is the case diabatic surface or diabatic state. Psi here is the adiabatic basis, and capital N is the total number of adiabatic bases or adiabatic states. So how to find this transformation matrix is very challenging actually in general. And this procedure is called diabatation. I will not talk about the diabatation in detail because this is actually still a very active field of research. But I will just give you one reference. There are many ways, actually many non-equivalent ways to do diabatation. But I will give you one reference. This is based on the configuration uniformity. So how to ensure that the diabatation, the diabatic surface you found actually has a consistent character. This is called configuration uniformity. The reference is This paper is by Nakamura and Chola, published on Journal of Chemical Physics. This tells you how to find such a transformation based on the configuration uniformity in general. Okay, so in the next lecture, we will talk about the general concept of adiabatic approximation. And I will talk about more about the barrier connection and the barrier phase, which is actually a very interesting physical quantity.